welcome back. In the second part of our reinforcement detailing, we're going to talk a little bit more about developmental length. Okay, so in the last video we kind of talked about the straight bar developmental length for bars that are in tension. Now we're going to turn our attention to what about bars in compression, okay, or what can I do to shorten LD as we go into that. All right, so again, we're back in ACI section 25.4.9. This is ACI 318-19. Okay, and so for a bar in compression, in order to be able to establish a particular length of this thing, okay, that the LDC value then is given by this formula, okay, which is Fy times psi r all over 50 lambda square root of F prime C, or the larger of 0.0003 Fy psi r dB, or 8 inches minimum, okay, in order to be able to develop a compressive length on there. Okay, also we cannot use a hook to reduce this length. We're not allowed to do that, and I'll explain what a hook is here in a little bit. Okay, all right, the modification factors for bars in compression is a very similar table. We're looking at 25.4.9.3 this time. Again, lambda is the same 1.0 for normal weight, okay, and then this guy is psi r, okay, and it's basically anytime it has to do with confining reinforcement, okay. Do I have stirrups that are within space or a spiral? Okay, so let's see, what are my values? I have reinforcement enclosed within 1, 2, 3, or 4, okay, or 1 is a spiral, and then they kind of define what that criteria is. So 1 is a spiral. If you're enclosed in a spiral, you get a 0.75 psi r value. Okay, if you're a circular, continuously wound tie with bar diameter greater than 1/4 of an inch, so larger than a number 4, and a pitch of 4 inches on those, okay, or a number 4 bar or a D20 wire ties in accordance with this particular provision that are spaced at less than 4 inches, okay, or hoops in accordance with 25.7.4 spaced at less than or equal to 4 inches on center. Basically, if your stirrups are less than or equal to 4 inches on center, then I can reduce that distance as well. And that's one of the reasons a lot of times at the bottom of a reinforced concrete column, you may have your anchor bolts coming up and doing this, and then I have these bars coming in as my splice, and they'll put in some very tightly spaced bars at the bottom or anywhere that connection, that splice is being done, because the splice is based on the developmental length, and I want to take advantage and get every little bit of this out that I can. So that 0.75, that's a 25% savings on this thing, right? And so you start to choose very, very small bars, and you do some things to try to make that happen, okay? And that's one of the detailing tricks that you'll see done on, on construction drawings from time to time. Okay, all right. So now what happens is, and what psi r is really doing is, the primary concern of bars and compression is not the bond stress and being able to develop the force. It's more about the buckling of the bar, okay? And this is the reason that, they made the comment that hooks don't matter. Okay, a hook is a bar that is straight, and then it has the end, this little leg. And what this leg does is, in a tension bar, it actually reduces the length that I need. If I pull on this with some force T, it reduces this length, okay, that is needed for anchorage, okay. In compression, I don't care what I have out here, because what we're doing is we're loading this bar, as this picture shows, in compression. So here, this dotted line indicates the straight bar. And what happens when I push on this thing is, if I put too much force into that bar, it will buckle and actually pop out the side of this, whatever the member is. It can actually buckle and spall off the concrete. Okay, this is one of the reasons that if all of a sudden I start putting ties around this thing, then those ties coming across here will help to hold that bar in place, and that's why I get that benefit of that 25%. Okay, and so again, anywhere you have a developmental length, it's generally a good idea to try to put a couple of ties in there at 4 inches on center, just to kind of help hold things together, literally, to keep that bar from buckling. Okay, all right. Other provisions, okay. Now, again, LD can get you into some trouble, these developmental lengths, okay. So they also have a provision, well, what if I put more bars in that are actually needed for strength? Okay, well, ACI says, okay, suppose you need 3 square inches of steel for strength, and your LD was 20 inches. would you really need 20 inches if I put in, say, double that amount of steel, 6 square inches? And the answer is no, okay? And ACI takes that into account and says, all right, well, we'll let you use a reduction ratio on this, which is basically the area of the steel that's required divided by the area of steel that you provide. Okay, and so this is allowed for both bars in tension and compression. It's basically saying I don't need the full developmental length if I provide more steel. And that's another trick for shortening this developmental length. Okay, but there are some exceptions to this rule that you have to be aware of before you start playing with this provision. This provision is located in 25.4.10. Okay, and and then some of the subsections start to kind of give you some things here. Okay, the first one is like any non-continuous support. This would be a simple end or something, or a case where I have to terminate a bar at the end of a beam. That's what they're talking about here, because obviously they don't want you reducing that too much. Okay. B, at locations where the anchorage or development for FY is required. Okay, so if you need FY instantly, then you can't all of a sudden reduce the area. Okay, or play this game where FY is required if you prove it by strength. Okay, where bars are required to be continuous. Okay, as in through a column, or this one gets you in trouble on some seismic provisions. Okay, where a certain number of bars have to be continuous through a section. For hooked, headed, and mechanically anchored deformed reinforcement, okay, I'm not allowed to reduce it. Okay, seismic systems and seismic design categories C, D, E, or F, these are the most severe of the seismic categories. You can't provide provision, and in fact, we haven't talked a lot about seismic requirements in this series. Seismic can really drive the way you design reinforced concrete, okay, and especially with the detailing. We've talked a little bit about stirrup supports and columns and those kind of things, but seismic's kind of a different animal. So by all means, don't use these provisions to try to do a seismic design. Okay, and then the last one is anchorage of concrete piles and concrete filled pipe piles to pile caps. Okay, and again, this is a seismic provision. They don't want the pipe cap breaking off of the pile that's connected to it. Okay, and so those are some of the reasons. But you can't. But otherwise, you are allowed to reduce it. Okay. All right. Okay. The next category that we have for reinforcement detailing is what happens when you have to cut a bar. Okay, and this has to do with tension splices, and this is found in 25.5.2. What a tension splice is, and I've got a picture of one down a little bit lower. We kind of hinted at it earlier. Is basically I have two bars. They're basically laid in side by side. Okay, and so this LST is our tension splice. I'm pulling on this bar this way, and I'm pulling on this bar this way, and we are not welding or tying these bars together. Okay, they're just kind of laid in side by side. Well, there's a minimum length that's required to assume that I can transfer the forces from one bar to the other. Okay, now if you came in and welded these guys together, they would be treated as a single bar, assuming they met the welding requirements. Okay, to be able to do this, and one of the reasons we have to do this is typically rebar comes in 20-foot lengths. Right, so if it's 20-foot length and your beam is 30 feet long, you're going to have a splice somewhere. So you have to figure out, well, where am I going to splice it, and then how do I splice it, and these are the details that are associated with that. So splices are very common. Now, splices fall into two categories, all right? The first one is a Class A, which is no more than 50% of the steel being spliced at a cross-section, okay, and 200% of the required steel is provided. Okay, so mainly that you've put a lot more steel than what you really need. That's considered a Class A. Okay, so for a Class A splice, LST is 1.0 times LD, and for and it's the greater of that value. So the LD is what we chose for, that we calculated in the last video. That it's the greater of that value or 12 inches, depending on the bar size. Okay, the Class B is basically any other case, and most of the time, for most problems that we're working on, we're doing Class B splices. Okay, it's just a little bit safer, but you'll notice that the difference is it's the greater of 12 inches, or now it's 1.3 instead of 1.0. Okay, so most of the time, whenever I'm detailing this, I go ahead and pay the price on the 1.3, and then I don't even worry about this table. Okay, this is by far the most common situation anyway, because often we don't put double the steel that we actually need. We might be a little bit over, but not a whole lot. So Class B is by far the most common. All right, the next area then is the one that can really make a difference in your developmental calculations, okay? And these come out of 25.3 and 25.4, and these are the standard hooks in tension. Okay, again, we cannot use a hook in compression, but there are some detailing provisions that you have to have on here. Okay, so standard hooks are used to provide additional anchorage when there is insufficient length to develop a bar. Okay, if we look at this, there are two different types of hooks that ACI will document as a minimum of 90 degrees or a minimum of 180 degrees. Okay, and so what we have is, and these are taken out of the ACI code, kind of the provisions of this, is they basically define a couple of parameters on this 90-degree hook. You can see that I'm pulling on this. This is my critical location that I have to provide a distance that they call LDH from here to that bar. Now notice there is a radius in here. Okay, and so the radius becomes a big issue on how we calculate all this stuff. But the LDH goes from the bar all the way out to this point. Okay, and then there is another dimension that goes from, it's basically the straight line extension after you come out of the radius. It's called LEXT. Okay, and so how you calculate this comes out of this table 25.3.1. Okay, for a number 3 through number 8, okay, the minimum inside bend diameter is 6 bar diameters. So that's the inside radius around here, the 6 bar diameter. So for a number 4, it would be you would have a minimum of a 3-inch radius that has to happen. And we talked a little bit about that when we were doing some of the detailing and the spacing requirements. Okay, for a 9, 10, or 11, it's 8 bar diameters, and for a 14 and an 18, it's 10 bar diameters. Okay, and then the straight extension, which is this piece of it, this LEXT, is 12 bar diameters. Okay, all right. If I do a 180-degree hook on this thing, okay, the dimensions, okay, the bend diameters are still the same, 6, 8, and 10 bar diameters. Okay, but your extension now becomes a whole lot shorter. It becomes the greater of 4 bar diameters and 2.5 inches, whichever one is longer. That's the amount that you have to have. Because what they're assuming is that by hooking this thing back around on it, that, you know, that the concrete that it's wrapping around is providing some restraint to help hold this in here. The other problem that happens in this is that back in the 90 degrees, if I pull on this on here and this point doesn't want to move, I can actually, by trying to pull this bar out, this thing wants to straighten out, and so this end can actually start to pop out a little bit. And if you're too close to the edge or have too much cover, that becomes a major consideration, that you don't want to spall that back side of this thing off if you're too close to an edge on that back surface. Okay, the 180-degree guy doesn't have that, and so they found that by making this a certain length, 12 bar diameters, that generally that problem is not as likely, that you have enough constraint or you lower the concrete stresses enough that it doesn't want to fail or pop out. Okay, all right, so the one parameter that's in here, the last one is that, and I know it's hard to see, that this is also LDH, so it's from my critical point all the way to the extreme edge of my bend. Okay, of my hook bar. Okay, so the hook development length is very similar in nature. Okay, now we've got, our LDH is Fy times psi E times psi R times psi O times psi C. And so some of these you've seen before, some you haven't. The formula is a little different. It's 55 lambdas over the square root of F prime C, and then multiplied by dB raised to the 1.5 power. Okay, or 8 dB if it's larger, or 6 inches if that's larger. Okay, so you'll always have at least 6 inches as a developmental length for a hook. Okay, all right. Okay, so once I do that, then there are so let's talk a little bit about some of the parameters. Some of them will look very familiar. Okay, so for development length of the straight bars, hooks are affected by some other factors. All right, so the first one is the coating factor. That's our epoxy. That's unchanged. Okay, we have confining reinforcement. Okay, and that kind of has to do with, any sort of transverse steel that's on this thing for a number 11 and smaller, okay, and a spacing that is greater than a certain amount, psi R is 1.0, otherwise you're going to use a 1.6. Okay, this provision is new in the 2019 version of the code. Okay, and there are some additional requirements that you'll want to make sure that you look at and make yourself familiar with. Okay, but that's this parameter here, this confining reinforcement. Okay. There is the location and the cover, okay, for a number 11 and smaller bar, okay, with side cover greater than 2.5 inches and in the core of a concrete column, or side cover normal to the plane of the hook, okay. Let's see. This is my psi O value. Where is my psi O on this table? Yeah, so for number 11 and smaller diameter, I'm reading up here, I think I left off in something when I wrote it out. For number 11 and smaller diameter hook bars, terminating inside column core with side cover normal to plane or a hook greater than or equal to 2.5 inches, or with side cover normal to the plane of the hook, there it is. Okay, greater than or equal to 6 dB. Okay, that's what I was going to say. I missed this piece of it. Okay, my SiO is 1.0. Most of the time, that's what you have. Otherwise, if you have a very thin problem, as we were talking about, this is that bar trying to pull out the back end of this thing. If that distance is, less than about 6 bar diameters, then you're going to get penalized 25% with the SiO that's happening down here. Okay, all right. All right, there is also a concrete strength factor. Okay, for these hooks, okay, if you're dealing with an F prime C that is less than 6,000 psi, then your size C is F prime C over 15,000 plus 0.6. Otherwise, if you're getting into high strengths, my size C is a 1.0 value. So you can actually get some savings for, for this. For example, if my F prime C on this is 5,000, my size C value is only 0.93. Okay, so you get some savings by going with weaker concrete. Okay. Now, these new requirements, one of the things that was kind of a surprise as I was preparing this packet and I realized they made these changes is that these developmental lengths can result in results that are 50% larger over previous versions of ACI 318. Okay, so, based on I guess there have been some problems, probably seismically related. It's a lot of times what drives all these provisions. But, that's a pretty substantial increase. It's not something to scoff at. We'll just have to kind of look at that. All right. Okay, now, there is some notes about the confining steel that we should talk about, okay? There are some placement rules. Okay, again, these images come out of the code. I'll point you at the sections. We won't spend a lot of time on these, but 25.4.3.3a and 3b have to do with confining steel that will help reduce your developmental length. Okay, first one has to do with horizontal bars in here that are closer than 8 dB over the length of the extension. Okay, then what happens is that, and the length of this is 0.75 LDH. Okay, these are the requirements. To be able to say that I have confining steel, you have to provide that. Okay, or I could do what would be more like a stirrup kind of thing. And again, it's the same provision, 8 dB over, 0.75 of LDH. These are all the requirements in order to be able to say you can't just throw one bar in and say, oh, got confining steel, we're good to go. There has to be a certain amount to kind of help hold that core together. And what this does, this provides kind of a clamping force around the bar as you try to pull it out. Okay, to kind of help resist that. Okay, as the bar tries to detract and try to pull through. Okay. Additional requirements. Okay, this has to do with some of the bending radius. Okay, when the side and extension cover is too small, especially at dead or discontinuous ends of beams, okay, splitting failures can occur. Okay, and so this is kind of some provisions for concrete cover that's required. Okay, that ties or stirrups are required over a length of LDH when I have and I start kind of tells you how to start the spacing, that my hook is here, that I have to go less than 2 bar diameters for the first one, and then I go 3 bar diameters spacings or less for all of the others. That's what's defined as the confinement for us there. Okay, and this provision also applies when you have less than 2.5 inches of cover on the end or on the top of this thing, because again, you can get a splitting failure as you try to pull that through. Okay. The other provision that's in there then has to do with the detailing of really stirrups. Okay, and you've seen some of this in the development of the hook, but for radiuses of stirrups, which aren't exactly full tension members, they are kind of. But there are provisions that, if I have a U-shaped stirrup that looks something kind of like this, and I have a crack that forms, and I start pulling on this direction, I want to make sure that I don't pull that end out. And so that's why you have the requirement that this thing has to be terminated in a hook of some sort, whether it's 90 degrees or turned around. And typically you want to put a bar under there to help hold that stirrup in place as the shear force tries to pull down on it. And that's what this table is going to do for you. And this is 25.3.2. So for a 90-degree hook, the minimum inside bend diameter is 4 bar diameters for a number 3 through 5. It's 6 bar diameters for a 6 through 8. Okay, and again, they only do small sizes because we're talking stirrups here. You don't make a number 10 stirrup usually. Okay, that'd be a big structure if they did. Okay, for 135 degree hooks, okay, it's 4 bar diameters and 6 bar diameters. It's the same provision. Okay, and then the 180 degree hook, the minimum inside bend diameter is still 4 and 6. So the minimum bend diameter doesn't change. It's affected by the bar size. What does change then is that straight extension. Okay, and so for a 90 degree hook, it was the greater of 6 bar diameters and 3 inches or 12 dB. For a 135 degree hook, it was the greater of 6 bar diameters and 3 inches. And for a 180 degree hook, it was the greater of 4 bar diameters and 2.5 inches. So your savings are really down here is predominantly what we're looking at for that one. All right? Okay. And with that, that gets us then to kind of our detailing exercise. Okay. And which is basically reworking the problem from the last exercise. All right, so if I pull this down a little bit, okay, it is again our cantilever option. Okay, and this kind of hints that if you worked the last example, you found that those straight bars wouldn't fit. Well, can we come up with a detail that will allow us to make this fit? And that's the process. So the first couple of steps are exactly the same. Okay, we're gonna we have number 8 bars longitudinally. Did I call out the stirrup size? I didn't. Okay, but we can kind of start to look at, assuming that it's a number 3 or a number 4, come up and compute the 90 degree hook developmental length detail. So we're going to look for LDH, LXD, and then the bend diameter, D. Okay, and would that fit within the cross section? Okay, and then we're going to have you compute 180 degree hook developmental length, and we're going to see, does that fit within the cross section? Okay, and then finally, so that gets the 180, so doing the same process. And then finally, I want to know what the maximum rebar size that can be developed in this 90 as a 90 degree bend in this particular cross section. And you'll find that, it has to do really basically with LDH, being 48 inches or less than 48 inches, okay? At some size, you're going to exceed that, and then you're going to know that I have to hook that bar, and that's one of the checks that I want you guys to be able to make. Right, and with that, I think that will take care of the last of our detailing options. Okay, so in this one, there's a lot of ground that was covered, obviously, but we looked at being able to develop bars and compression, but more importantly, probably the most important thing to pull out of this is the hooks. Okay, hooks are they are a saving grace when it comes to detailing concrete, right? That I can greatly reduce my developmental length, sometimes by as much as a half or 2/3, depending on the size of the bar and some other considerations, and then some other things that I can do to help reduce that particular value. Okay, so anyway, I hope it's been clear. If not, please leave me some feedback down below in the comments. And then, as always, be sure to like the video, give us a thumbs up if you would, and of course, as always, subscribe to the channel. We would greatly appreciate it. And with that, we will bid you all a fond farewell. Have a great evening, and we will see you guys next time. Happy engineering.